Hello, my name is Aaron. This is my Project 6 presentation for CE570. The goal for this week's project was to define a deformation map for the 3D body of our choosing, to compute the tangent vectors on the undeformed 3D body of our choice, to compute the deformation gradient or the tensor field of the deformation map, and then to define some 3D curves along our body, and then to verify one of the lengths of the deformed curve after deformation has taken place. So below here, I've just highlighted my deformation map and my vector field definitions for my 3D body of my choice, and you can see that my deformation map on the right there translates very closely to my vector field on the left, where I've just replaced all the appropriate x locations with the appropriate z values, and then added z1, z2, and z3 to the appropriate rows of the vector. And then below there is just the code highlighting the deformation map that plots in MATLAB. In this slide, I have just highlighted my tangent vectors to each one of my three-dimensional surfaces. And as you can see, the definition of those tangents are just the partial derivative of my parameterization with respect to one of the variables that makes up the parameterization of that surface. So you can see my tangents highlighted here for my hollow cylinder, and you can see my tangents highlighted here for my hollow hemisphere. And then you can see my appropriate lines of code that reflect those tangents for each one of my 3D surfaces. Moving on, as you can see here, this is just the definition of my deformation gradient or my tensor field that's applying itself onto my silo. And as you can see, this is just the definition of my deformation gradient, which is just the partial derivative of my deformation map with respect to z1, z2, and z3 at the appropriate locations within the tensor. And after working through that math, as you can see with my deformation map up above here, results in a deformation gradient as shown here. And in order for me to effectively code this into MATLAB in order to be applied to each one of my 3D bodies, I just need to replace the z1, z2, and z3 with the appropriate locations of my parameterization of that 3D body. So for example, for my hollow cylinder, I would just replace the z1 coordinate with the appropriate x1 coordinate of my parameterization of my body, and so on and so forth for my hollow hemisphere. Moving on, now I'd just like to demonstrate my code running appropriately. So here I have my code defined. You can see all my input parameters here for R1, R2, and H for my hollow cylinder and hemisphere. So right here is my code for my hollow cylinder. You can see all the appropriate parameterizations as well as my definition of my map and my tensor field. And then here's part 2 where my hollow hemisphere. You can see the same appropriate lines of code, but for that respective shape. And then finally my vector field, and then we'll give this a run. It takes a while to run because I have a rather complicated vector field or deformation map. And as it's running, you can see the outputs highlighted here of my undeformed and deformed lengths, as well as you can see my graphs as plotted. And you can see my 3D body but in the undeformed and deformed stages, and you can see that all the appropriate line work that's being plotted on top of the deformed line or deformed body, so I know that my code is working appropriately. Finally, we were tasked with choosing one of the lines that's plotting on our 3D body and calculating its deformed length. So as you can see, I've highlighted part 1, curve 5, so this curve, this straight line that you can see right here that's going up the side surface of my hollow cylinder, and the deformed stage over here, this is the line of choice that I will be calculating the deformed length. And also you can see all the other definitions of my other curves and the appropriate code within MATLAB. Finally, in order to calculate the deformed length of the curve of my choosing, we have to parameterize the undeformed length first, and as you can see I have that defined here of R2, 0, and S in the x1, x2, and x3 dimensions respectively, where R2 is just the constant outer radius of 20, and S varies from 0 to H, which is just the height of my hollow cylinder. And as you can see, that results in an undeformed length of 12, which exactly matches my MATLAB output. And then in order to calculate the deformed curve length, I have to plug in the appropriate parameterization locations into the appropriate locations of my deformation map, and then take the derivative of that map with respect to S, which is just the tangent vector of the deformed curve. And doing that, as you can see in this image here, results in a vector that looks like this. And then I need to take this vector and find the total magnitude of it, and then integrate that from 0 to H, because that's what S varies from. And as you can see, plugging that into an online integral tool, because it's a very complicated integral, results in a value of 10.5583, which exactly matches my MATLAB output. And then you can further see that these values here are exactly matching for my hollow hemisphere and my hollow cylinder, leading me to believe that my code is working as it should be. Thank you for watching.